Okay, let's just get started. Let me start recording here as well. Yeah, I don't know where the rest are. But we're gonna get started either way. So, welcome to those who could join us. Minority of the group, but we're going to continue either way. Hopefully you guys can see this okay, but as usual I am recording on the other camera and I'll post this to YouTube late tonight / tomorrow morning. We had an example that we wanted to get into last time, finding the Maclaurin series as well as the radius of convergence, and I don't know why I wrote out integral of convergence. Normally I'd write out IOC here. But whatever, that's IOC of the following functions. The first one was e to the x, the next one is cosine x, and the other one is sine of x. So yeah, as always I'll do the hardest example, so I'll do the first one, e to the x, and then someone else can probably help me with cosine of x. Welcome Kimberly. And the last one, probably after doing these two, I won't do the last one. The one for sine of x is going to be very similar to the one to cosine of x. So once you see how cosine of x works, I'll just tell you about the sine of x function, and it pretty much almost identical, almost, of course, the solution to b will be almost the same thing. So let's actually just continue. So we're going to find the Maclaurin series as well as the radius of convergence for these three functions. So let's actually begin. So A. So to remind you last time, just how this actually is going to work, what formula we're going to use. So last time we spoke about something called the Taylor series of a function. So we got a Taylor series. This was the series n goes from 0 to infinity, of f to the n evaluated at x naught divided by n factorial times x minus x naught to the n. This is called the Taylor series of f of x centered at x naught. And we also spoke about something called a Maclaurin series. And it was just a Taylor series where the center point is 0. So for the Maclaurin series, we had to find this guy, the nth derivative evaluated at 0 over n factorial times x to the n. So this is the guy that we're going to do essentially for the three functions, e to the x, cosine of x, and sine of x. So we're going to start with e to the x. Now, as we know here, this is supposed to model an infinite polynomial, whatever that means, and we'll talk about that a little bit more today. So the x to the n is always just going to be x to the n. We're going to see all the powers of x, what it happens. X to the 0, x to the 1, x to the 2, that's not going to change. The n factorial also is a part of the formula that's not really going to change. That just counts 0 factorial, 1 factorial, 2 factorial. So when we want to actually discover what these series look like for an individual function, the part that we focus on is actually the derivative part. This is the part that's going to change for the particular function. So once we want to figure out what the nth derivative evaluated at 0 looks like in general, or maybe even one at a time, we just plug it into this formula for each n value. And that is actually going to help us find the Maclaurin series. So that's what we're going to do. So I'll show you guys how to get this done with e to the x. then maybe someone can help me with the cosine of x function. Yeah, so remember the original function? This is like saying the 0th derivative. So this is really f to the 0 of x. And so I want to find what it looks like evaluated at 0. So this means f to the 0 evaluated at 0 is, I just plug in 0 for x. This is e to the 0, which is 1. Now I find the first derivative. Well, that's just e to the x. And so I'm going to find the first derivative evaluated at 0, which is 1. Then I'm going to find the second derivative. That's e to the x. This means if I take the second derivative evaluated at 0, the answer is 1. Now, pretty much what you do is you do this long enough so that you can kind of see a pattern going, and I think we can all already see the pattern that's happening. It's literally always going to give us 1. So I can talk about in general, and you won't always be able to do this, but in this case we can. We can talk about in general what the nth derivative evaluated at 0 looks like, and for the function e to the x, it's 1. It's always going to be 1. So then what I can do now is just, that's a general formula for the nth derivative. Take that guy and plug it in here, in this position. So this gives us the Maclaurin series of e to the x. Well, that's just going to be the series n goes from 0 to infinity of, well, 1 over n factorial times x to the n. Or in other words, x to the n over n factorial. N goes from 0 to infinity. And that's your answer. So that is the Maclaurin series for e to the x. Now, something else that you would probably notice here is that that's actually a previous example. If not in the last class, the class before that. This was one of the examples for which we already found the radius of convergence and the interval of convergence. And this guy worked everywhere. The radius of convergence was infinity, and the interval of convergence was minus infinity to infinity. This is from a previous lecture. So, kind of get that for free. You can look back in that lecture. We'll actually do some more practice of finding this on the other functions. But so far we have that. By the way, this guy, if you were to write it out, and I believe the last time we spoke about this, we actually wrote it out. It looks like 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. And we have that guy. Any questions so far? No questions? We're all good? Everyone understands so far what we did? Guess there's no questions. So maybe then what we would do is work through the other one. So this is the Maclaurin series of e to the x. And I'll talk about the relationship between this guy and e to the x a little bit more. A little bit later. I don't know if I want to do that before section 10.10 or after. Let's do it for the second example, B. Cosine of x. So remember the formula, the series n goes from 0 to infinity of f to the nth derivative evaluated at 0 over n factorial times x to the n. This is the guy we're looking at. And of course, the other part that changes here for the particular function that you're looking at is what the nth derivative looks like. It's always going to be pretty much x to the n over n factorial, and we want to fill in this part here. So maybe someone want to tell me how we do the one for cosine. How do we build that guy up? Well, yeah, you start with cosine of 0. So first thing you do is you find f evaluated at 0. Well, that's cosine of 0, which is 1. Okay, what do we do now? Take the derivative. Derivative of cosine is minus sine. And then well, minus sine of 0. Then you evaluate it at 0. So you would have f prime at 0. And so that's just minus sine of 0. Sine of 0 is 0. And the idea is now you rinse and repeat. You keep doing this until you can see a pattern. So you find the second derivative. That would be minus cosine. This means second derivative evaluated at 0 is minus 1. Okay, I'm not sure I see a pattern yet. Let's do the third derivative. This is positive sine. So the third derivative evaluated at 0 is 0. Let's do the fourth derivative. And that's cosine. So the fourth derivative evaluated at 0 is, well, it's actually the same as the first step, is 1. And now you can kind of see here that this pattern is just going to repeat. Which pattern? Well, this pattern specifically. 1, 0, minus 1, 0, 1. Then the next one is going to be 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0. That pattern is going to keep working. So now the question is, can we figure out what would the nth derivative look like? Some sort of general formula here. Ideas? Well, it's not 1, because it literally changes value. 1, 0, minus 1, 0, 1, 0, minus 1, 0. It's not always 1. Yeah, well, saying it ends at 1 is it's kind of weird saying that it ends at 1 because it doesn't really end. It just keeps going forever, right? So it just goes 1, 0, minus 1, 0, 1, 0, minus 1, 0. It keeps going. Like this is going to keep happening, right? So that's what I meant by pattern repeats. But I want a way, hopefully there's a nice way to actually write down in general something that would give me this pattern. Can we think of anything? Let's move this dialog box out of the way here. So you see a -1 to the n. But that doesn't happen everywhere. So it happens here, here, here. If you only focus on the non-zero parts, you see a 1, then a -1, then a 1, then a -1, then a 1. So yeah, it turns out if you focus on the guys that are non-zero, like this guy, let's do here, this guy, well, together those guys have a pattern, -1 to the n. Now here's the thing. Because what these guys are doing, they're giving us coefficients of a polynomial. Essentially what you can do is you can think of a polynomial where some of the coefficients are 0. What you can do is you can essentially ignore those guys, ignore the coefficients that give you 0, because they're not even going to be in the polynomial that you're writing down. So it turns out that what we can do is we can kind of ignore these guys and just build a pattern over the guys that don't give us 0. And you'll notice that once we're not at the 0 points, the things just change like -1 to the n. So when n is 0, you get 1. When n is 1, when n is 2, you get -1, and so on and so forth. So if I ignore these guys, here my n is counting non-zero coefficients. So who do we ignore, who do we take? How do we know? What's the pattern? Who are the guys that don't give us 0? If you had to describe it somehow. Well, n not equals 0? No. Like when the output is not 0, how would you identify when that happens? What do you notice is happening here? That's okay. Another idea? So here's the question. If you wanted to ignore the zeros, can you describe to me in a phrase, in a word, in a formula, when we see this pattern -1 to the n? Give me something that tells me who should I ignore or who should I pay attention to. Where does this pattern actually fit? Sure, you ignore all the guys that give me sign, but again, we want it in terms of like a series, because we're counting. So, right, you ignore when n is odd. That's the thing. So this happens. So you'll notice that the pattern works. This pattern works for even powers of x. So that's the thing. So once we figured out a pattern here, ignore all the odd guys, and the even guys are actually going to give us this pattern. So that allows us, and I'll give you a second to take a snapshot here, because I'm going to erase this and actually write down what the answer is. So that allows us to actually write down a pattern for the general formula. So this means Maclaurin series for cosine of x is here's the pattern that we found for the derivative. It looks like minus 1 to the n. But we know that it only works where n is an even power, where only the even terms follow this pattern. So instead of writing x to the n, what I can do is I can write x to the 2n. And then to show that it only works for even numbers, in the denominator, I write 2n factorial. Now, notice what that's actually going to do for us. This will mean that when I plug in 0, I just get 1. When I plug in n equals 1, I would get the minus x squared. Plug in n equals 2, I would get the plus x to the 4th. Plug in n equals 3, I get minus x to the 6th. Notice here, by making these guys 2n's, it forces only the even guys to get spit out. So we have the x to the 0, the x squared, the x 4th, x 6th, x 8th, x 10th, and so on and so forth. We can essentially ignore all the odd guys here because we know, well, maybe at some point you would have seen this, but basically the definition of even means you look like 2n for some integer n, right? So every even number can be written as 2 times some integer, and every odd number can be written as 2n plus 1. So we realize the minus 1 to the n pattern only works on the even numbers. So I write down the pattern, minus 1 to the n, but then to force only the even numbers, I change all other n's in my formula to 2n, because 2n will spit out all the even numbers. Any questions on that? So that's actually that's the Maclaurin series for cosine. So it's going to be the series. N goes from 0 to infinity. Minus 1 to the n, x to the 2n over 2n factorial. That's how you compute that one. So so we only use our power the formula for the Maclaurin series on the even powers. And once we're on the even numbers, the pattern is minus 1 to the n. And yeah. So that's the first answer. So now what we want to do is, that's the series. Let's actually find the radius of convergence and the interval of convergence of this series. So ROC and IOC. So how do we go about finding the radius and interval of convergence of a series? Anyone? Bueller? Brain is not dysfunctional. Remember, this is last lecture, maybe a couple lectures ago, when we found the when we were finding radius of convergence and interval of convergence, and I was like, you always do this thing. And then the ratio test. Yes, the ratio test. You always go with the ratio test. So pretty much by the ratio test, we're going to take this series, plugging in n plus 1s for all the n's, then divide it by the original series, and take the limit as n approaches infinity, and force that to be less than 1. So Should I write that out? So we're going to compute L, which is the limit as n approaches infinity of the absolute value. Now, of course, I can ignore the minus 1 to the n. We already spoke about that. It's absolute values. They're going to kill all the signs here. So this is x to the 2n, 2 times n plus 1, divided by 2 times n plus 1 factorial, divided by this guy, which I can think of that as multiplying by the reciprocal. So this is 2n factorial over x to the 2n. Now, let me clean that up a little bit so you can see. This here is x to the 2n plus 2 over 2n plus 2 factorial times 2n factorial over x to the 2n. Can anyone tell me how to simplify that? How does that simplify? You see, was I blocking the? Ideas on how that simplifies? But yeah, you group them. So we have the limit, let's put all the n's together, 2n factorial over 2n plus 2 factorial, then group all the x's together, so this is x to the 2n plus 2 over x to the 2n. Now do you see anything you can take advantage of? Right, so that's correct. So x to the 2n. Oh, Ashif just joined. Okay, so x to the 2n cancels into the x to the 2n there, so I'm left over with an x squared. Now, you said that this was 1 over 2n plus 2 times 2n plus 1. How'd you get that? Well, bigger and smaller factorials, I'm not sure if you know what that means.
Yeah.
Hello? Right, so remember the 2n plus 2 factorial looks like 2n plus 2 times 2n plus 1 times 2n times 2n minus 1, going on forever. It's actually this guy. So the 2n factorial cancels into this, but it cancels this part, and so we're left over, it cancels into that 2n plus 2 times 2n plus 1 times. So this here is just pretty much 1 over 2n plus 2 times 2n plus 1. And that's because this is true. So now, what is that limit? It is 0. So remember, the limit is as n approaches infinity, which means, as far as limit is concerned, your x squared is just a number, it's just a constant, it's not actually changing the x's, it's only changing the n's. But I have 1 over this guy, the denominator is getting huge, the numerator is staying still, it goes to 0. Now, what does it mean when the limit goes to 0? And David has finally entered the room. David, what does it mean for the limit if the limit goes to 0? This one right here. So we're doing the radius of convergence for the cosine guy. We plugged it into the ratio test. We did our simplifications. Turns out that the limit goes to 0. You're rolling dumplings. No, it's not inconclusive. Remember, the ratio test is only inconclusive if the limit gives us 1. Right, 0 is less than 1, so what does that mean? This is less than 1 pretty much always, right? Now, we got the limit is 0, which is always less than 1. Now, here's the takeaway from that. It means the particular x value that I chose doesn't actually matter. It doesn't actually mean anything, which means I can pick any x value I want to plug in here, which essentially tells you that the radius of convergence is infinite. I can plug in any number on the real line. And so the interval of convergence is the entire real line, minus infinity to infinity. So that's this answer here. So this guy actually works like the Maclaurin series for e to the x. The radius of convergence is infinity, and the interval of convergence is the entire real line, minus infinity to infinity. I can plug in any x value I want, and this series that I had before, which I erased, the series is going to converge. So let's summarize what we found. The Maclaurin series of cosine of x is n goes from 0 to infinity of minus 1 to the n x to the 2n over 2n factorial. This gives us the pattern of plus 1, minus 1, plus 1, minus 1, plus 1, minus 1 on the even guys. And the radius of convergence is infinite, and the interval of convergence is the entire real line. We can plug in any x value we want, and that series is going to converge. So that's the answer to part B. Now, because the one for sine of x is so similar to cosine of x, obviously you differentiate sine, you get cosine, then you get minus sine, then you get minus cosine, then you get sine. It also has a repeating pattern. All the sines are going to give you 0 when you plug in x equals 0. All the cosines are going to give you 1 when you plug in x equals 0. So it also has the alternating pattern. So it turns out we're not going to derive it. So I'll just tell you the answer for part C. It's very similar to the one for cosine. The difference is it's one step behind, or one step ahead, or however you want to think about it. The pattern is only going to work for the odd integers. So for C, if your f of x equals the sine of x, the Maclaurin series is, it's going to be minus 1 to the n, x to the 2n plus 1, like I told you, that's how we can indicate odd integers, over 2n plus 1 factorial. And its radius of convergence is infinite, and the interval of convergence is the entire real line. And that is for the sine function. Okay. Right. So you guys can practice actually writing that out for the sine, going through the process for the sine function, but that's what you would end up with. Now, do I want to mention this now? It's kind of weird to mention this before section 10.9, but I'll mention it, and then we'll kind of backtrack and justify some things. I mean, we're not fully going to justify it anyway, so it's fine if I just do this, I think. And I'll recopy this stuff as well, because it is stuff that you should know by heart. So let's actually do that. Now, we'll discuss what this means later. But the above three examples in the above three examples, the functions are equal to their power series. That means I can think of e to the x as the series that I wrote down for e to the x. The sum from n goes from 0 to infinity of x to the n over n factorial. I can think of cosine as a series. I can think of the sine as a series. I can think of, in fact, this is also true for 1 over 1 minus x, which we got from a geometric series. That one didn't have an infinite radius of convergence though. That only worked for x between -1 and x between -1 and 1. But what I want you to understand is for the e to the x, the cosine of x, and the sine of x, the series that we just derived, I can actually think of them as being equal to the series that I derived, and I'll talk about what that means in a little bit. Basically, it means that this series converges to that function. And in the same way, the Maclaurin series, the three Maclaurin series that we just found, actually converge to the function that they're representing. And we'll discuss that in 10.9, which I'm going to do pretty much right now. It is important that you know these. So we're going to explore this a little bit more in a little bit, but just know that these guys are equal to their series. We're going to talk about what that is, and it's also important that you know these, meaning from now on, these four examples, the Maclaurin series for e to the x, the Maclaurin series for sine x, the Maclaurin series for cosine of x, the power series for 1 over 1 minus x, these are things you should know by heart, and you should also know where they work. So here is what you need to know. So in terms of power series that you should know by heart, I expect you to know these by heart. So These, from now on, this is just something that we know now. We know this off the top of our head. The power series, So one of them is 1 over 1 minus x. We know that that is the series, n goes from 0 to infinity, of x to the n. We should also know that the radius of convergence for that guy is 1, and the interval of convergence for that guy is minus 1 to 1. So it works for all x values in between minus 1 and 1, not including the endpoints, and which means its radius of convergence is 1. So that's one guy that you should know by heart. The other guy you should know by heart is, of course, e to the x. E to the x is x to the n over n factorial. That guy has a radius of convergence of infinity. The interval of convergence is the entire real line. Okay. Now I write e to the x equals this, and that's something I'm going to talk about in a bit. And I really mean equals here. Like, this series and this function should be considered exactly the same thing. They're one and the same. This is just another way of writing that guy down. In the same way that 1 plus 1 is just another way of writing 2, this series is another way of writing e to the x. And there's all sorts of applications that we can take advantage of because of this, but we're going to talk about what that means in a little bit. So the power series for e to the x, the Maclaurin series, you should know what that is by heart. You should also understand that it is equal to e to the x. So for cosine of x, its Maclaurin series is n goes from 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. This guy has a radius of convergence of infinity, and the interval of convergence is minus infinity to infinity. So we just derived that guy as well. And again, I want you to think of this series as this function. They are one and the same. We're going to talk about that. Mathematically speaking, these two things are indistinguishable. They're different ways of representing the same function, the same idea. Sine of x is the series minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This guy has a radius of convergence of infinity, and the interval of convergence is, of course, the entire real line minus infinity to infinity. So these four things, which I'll get out of your way, you can take a snapshot at maybe 3, 2, 1, snapshot. These four guys, 1 over 1 minus x, 2 e to the x, 3 cosine of x, 4 sine of x. These are four power series that you should know by heart. You should know what functions they represent. You should know where they are actually valid. Now, it's easy for e to the x, cosine of x, and sine x. Any x can work, you don't have to worry about it. However, if you're representing 1 over 1 minus x by this guy, it does not work everywhere. You should know that that's only true if your x is between, if your absolute value of x is less than minus 1. Yeah, so that is just something we know now. So take a picture of that, write it down. And this idea of saying that this function equals that series, that's what we're going to kind of go into next. We're going to do it in a little bit of hand-wavy fashion because there are a lot of things in this section that our syllabus just skips over, and it's a lot of proof-based things, things that you wouldn't expect a Calc 2 student to know anyway. So what I'm going to do is I'm just going to tell you some facts, do some explanations, not going to really prove anything, but talk about some theorems. I'll also actually mention a theorem that the syllabus says to omit, but I think me just mentioning it is actually going to give you some more insight. So I'll just mention the theorem, and it'll give us more insight into some other things that I want to explain. So that's what we're going to do next. We're going to go into the next section, 10.9. So this ends 10.8. Takeaway from this section is you need to have these 4 things memorized, as well as the process of actually creating a guy like this. You should know how to do that. So know how to take n derivatives, find a formula for the nth derivative, evaluate it, come up with a pattern, and actually construct this series from scratch. That is something that you're expected to know how to do. That being said, let's actually examine a little bit more of what it means to be equal to a power series. And Taylor series was just one way to develop a power series for a function that we don't really know about some other series to connect it to. Last time we actually found a bunch of power series by knowing this one by heart. So we found the power series for 1 over 3 plus x, we found the power series for ln of 3 plus x, we found the power series for 1 over 3 plus x all squared, just by knowing this guy. But we couldn't do that with these guys because we couldn't see a relationship between them and this, but Taylor's formula for Taylor series actually allowed us to actually find formulas for these. Now, what I want to talk about is 10.9, where we're going to discuss convergence of power series. Of Taylor series specifically. So like I said, a lot of this, it's just theoretical background. So you'll never have to prove any of this, but it's kind of some things that you would be expected to know at this point. So we are going to talk about those. Yeah, so let's just jump into it. What is the first thing I want to just give you some definitions here. I'll talk about Taylor polynomials. Definition. Let f of x be a function at least n times differentiable. Now I spoke about one of the requirements for a Taylor series last, did I? I don't remember. I'll probably mention it again. But one of the requirements for being able to find the Taylor series of a function is that it has to be infinitely differentiable. You have to keep being able to take derivatives, which not all functions behave that way. We'll get to that in a second. Yeah, suppose you have something that's at least n times differentiable. Then its nth degree Taylor polynomial is given by so it's just a finite Taylor series, just that goes up to the nth degree. So it has n plus 1 terms, and it just has f to the n of x naught, x minus x naught, that's the center point, over n factorial. Let's put another letter here, because we'll go up to n, so it looks like something you've seen before. F to the k, k factorial to the k. K goes from 0 up to n. So this looks like, well, it looks like f to the 0 evaluated at x naught plus f prime at x naught, x minus x naught over 1 factorial plus f double prime at x naught, x minus x naught squared over 2 factorial plus dot dot dot. It goes all the way up to the nth degree. So f to the nth derivative at x naught, x minus x naught to the n over n factorial. So it's a finite polynomial. It has n plus 1 terms, right? So I'm just taking the Taylor series, but I don't let it go off to infinity. I just let it stop at some number n, right? This is called the nth degree Taylor polynomial. So it's just essentially the first n plus 1 terms of a Taylor series, right? So for a function, the Taylor polynomial centered at x0, if you want to be technical, is that guy. Now, another way that you can think of this intuitively, is it's kind of like the n plus first partial sum of a Taylor series. And just like when we had partial sums, that discussion, there was something known as a remainder term. So let me define that for you. So you can take a snapshot of this. 3, 2, 1, snap. And then I'll give you another definition. So this is the first definition. What is a Taylor polynomial, an nth degree Taylor polynomial? Well, this is it. It's just a finite Taylor series. You only go up to the nth power. Do I want to give an example of that? Yes. Notation. We often use p sub n of x to represent the nth degree Taylor polynomial. So, example, let's say your f of x is e to the x. Then I can talk about p sub 5 of x. The fifth degree Taylor polynomial, well, that would just be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus x to the 5 over 5 factorial. Right, so it's just a fifth degree polynomial. Just the first 6 terms of the e to the x Taylor series. Definition. Suppose this f to the n of x naught n factorial is a Taylor series. Then it can be expressed as so n goes from 0 to infinity, f to the n of x naught over n factorial times x minus x naught. We can write this guy as p sub n plus another polynomial, r sub n, where r sub n is called the nth remainder term. Or some people just call it the remainder term. They don't. So the remainder term of a Taylor series is just everyone after the nth Taylor polynomial. So that's just like the tail. Okay. So I'll give you some time to snapshot that. I'll write down a little example here. Three, two, one, snap. Okay, so that is i.e. if I have this guy, n goes from 0 to infinity, of f to the n, x minus x, evaluated at x naught, x minus x naught to the n over n factorial. This I can write down as, well, f to the 0 of x naught plus f prime x naught times x minus x naught over 1 factorial plus dot dot dot. I can go up to the nth derivative, f to the n of x naught, x minus x naught to the n over n factorial. And then I can continue, plus f to the n plus first derivative at x naught and I can just keep going, plus dot dot dot. And the first part is called, up to the nth term, this is called the Taylor polynomial, p sub n. This is equal to the Taylor polynomial, nth Taylor polynomial. Which is essentially the nth partial sum, or n plus first partial sum and the tail, pretty much everyone else going on forever for infinity, that guy we call r sub n, the nth remainder term. So, as an example, f of x equals e to the x, then its fifth remainder term. I already told you about the fifth degree Taylor polynomial. Well, this is just everyone after the fifth degree. So this is x to the 6 over 6 factorial, plus x to the 7th over 7 factorial, plus x to the 8th over 8 factorial, and then that keeps going. So we have something called a Taylor polynomial. It's just the first part of a Taylor series for a function going up to the nth power. It's called the nth degree Taylor polynomial. Everyone else, the tail end, which will have an infinite number of terms, that is called the remainder term. So if you write out what e to the x is, the first 5 up to x to the 5th is the fifth degree Taylor polynomial, R5 is everyone else. So those are just some definitions. Now, there is something called Taylor's formula. I want to tell you about this guy. Well, I'm going slightly out of order here, but maybe I want to tell you about some facts about the remainder term. So the first one I want to mention is a theorem. It is actually called Taylor's formula. So let f of x be an infinitely differentiable function on an interval I containing x naught. Right? So on some interval, for all x values in that interval, I can just differentiate my function infinitely often and all the derivatives will be continuous. Then turns out that your remainder term, that infinite tail, can actually collapse into one guy. We can get him to look like f to the n plus first derivative evaluated at x naught, evaluated at some number c, x minus x naught to the n plus 1 for some c to the n of x, for some c in the interval so essentially c is someone close to x. Close to x naught, there's going to be a value that when you plug it into the n plus 1, there's going to be a single term that is going to be equal to that infinite tail. You just have to find a specific value to plug into the derivative and to give that. Now the next thing is another thing that I think is nice, which technically I'm supposed to skip, but it's actually a nice thing that's going to help you see how what I'm going to write on after can actually work out. So there's another theorem. It's called Taylor's inequality. It turns out that there's actually an inequality that the remainder term will satisfy. So it says the following: if your n plus first derivative is less than or equal to some positive number m for all x minus x naught less than d, then the magnitude of your remainder term is going to be less than or equal to m times the magnitude of x minus x naught to the n plus 1 over n plus 1 factorial for this guy. On the same interval where this is true, you find an interval surrounding x naught where your n plus first derivative is bounded above by m, then your remainder term is going to be bounded above by this expression. And these are absolute value signs here. And this is called Taylor's inequality. So Taylor figured out a single formula, a single term that he can use to approximate, and it will pretty much be equal to the infinite tail after the Taylor polynomial. And he figured out an inequality that that tail would actually obey. If you can bound the n plus first derivative on an interval, you can bound the remainder term on that interval as well. So that is called Taylor's inequality. Now that can give you some insight into the thing that I'm going to mention now, which I guess you can think of as a theorem as well, but I don't think it has a name. Theorem. Let f of x be a function that has a Taylor series on an interval I. That means it's infinitely differentiable on I, all your derivatives are continuous on I, and you can pick any point in I to be a center point of that thing, and your Taylor series will converge to something meaningful. So it'll obey the ratio test on that interval, and I can infinitely differentiate f. So f is just a function where I can find a Taylor series on some interval. Then, if the remainder term approaches 0 as n approaches infinity, right? So if the form for your remainder term will go to 0 as n goes to infinity, then we can say that then the Taylor series f to the n x naught x minus x naught to the n over n factorial, n goes from 0 to infinity, we say converges to f of x. And we write f of x equals on I. So this is kind of the main thing I wanted to get to, but I had to define some terms for you before. So the idea of a Taylor series converging to a function, right? This is the idea that I can write a function as its Taylor series. Once I'm in an interval where this series behaves itself, I can think of the function as the series. They're one and the same. This kind of thing actually happens for all the examples that we saw before. The 1 over 1 minus x, for the cosine x, for the e to the x, for the sine of x. All their Taylor series, their remainder terms actually approach 0 as you go off to infinity. And for the e to the x, that's easy to see because the term is always 1. So pretty much any m larger than 1 is going to work there. If you look at for sine and cosine, those guys are also bounded above by 1, so I'd be able to find a number there. So I'd be able to bound this. So why this is important is because this kind of gives you an idea of how you would even know that something like this would happen. How do you know that the remainder term is going to go to 0? Well, if I can bound it by something, and looking at that thing, it goes to 0, then I know that r originally goes to 0 as well. So this was something that we looked at a long, long time ago. If the absolute value of a sequence approaches 0, then the sequence itself approaches 0. So you can think of Rn as some sequence, and it's bounded above by this guy. If you can tell that this guy approaches 0 as n approaches infinity, which is going to be a lot easier to do with that than some random formula here in general, then you will know that r approaches 0 as n approaches infinity. Whenever that happens, it means that your Taylor series converges to the function, meaning the more terms you add to the series, it keeps getting closer and closer to the function, and if you write down the infinite series, it is considered to be equal to the function. They are one and the same. This is just another way to write down whatever function you're looking at under this condition, which is pretty cool, pretty important. We're actually going to see some applications to this next time. But when would a Taylor series actually equal to the function that you use to generate the Taylor series would be when this actually works out. And it's a more important fact than we will actually see right now. But I just thought I would mention all of that stuff. Maybe I can give you some non-examples at this point for a little bit. So these are just some things to know. Now, as I mentioned last time, you've been doing college calculus, college algebra. Pretty much up to this point, almost every function you've encountered is infinitely differentiable, and almost all of them kind of behave themselves. So you might wonder why was this even a requirement? Are we ever actually going to be in a situation where the Taylor series isn't going to work out and it's not going to be equal to the function it's representing? So I'll give you some non-examples. So let's answer the question, what could go wrong? What could possibly go wrong? So here's an example of, oh, do I have a question? Can't wait for one of these functions to blow up. I'll show you a function that kind of does blow up. I'll also show you a function that essentially behaves very nice, but a Taylor series is still useless. And I'm going to show you a function where it actually, you can't find a Taylor series for the function. So here's an example. F of x equals the absolute value of x cubed. It turns out that you actually cannot find a Taylor series for that function. It doesn't exist. Now, you might wonder why, but you can kind of see what will happen if, well, I shouldn't say Taylor series in general. A Maclaurin series for this function won't exist, specifically at 0. 0 is the bad point. If I take a bunch of derivatives, you can actually compute it by hand, use the piecewise definition for absolute value of x and all that good stuff. You'll realize that you would get the first two derivatives are going to behave nice. Once you get to the third derivative, you now are going to have some constant times the absolute value of x, and we all know that the absolute value of x is not differentiable at 0. So here, if you look at f of 0, you get 0. F prime of 0 is going to be 0. F double prime of 0 is going to be 0. Once you go to f triple prime of 0, does not exist. That guy is just going to be some constant, like 6 times absolute value of x, which we know absolute value of x is not differentiable at 0. So this guy, not infinitely differentiable. Here's a guy where I can differentiate 2 times on any interval containing 0, but I can't do it a third time, right? And you can imagine if I went higher with the power, you can create other examples. So you could create a function that you can only differentiate 12 times and no more. Or you can only differentiate 100 million times and no more. Here's an example of a function that you can only differentiate twice, and after that it does not make sense on any interval containing the origin, because the derivative is not going to work out there. So this guy, you can't find a Maclaurin series for it. So the Taylor series actually doesn't work out. And the problem is, it's not infinitely differentiable. It's a guy that will have different, where eventually you can get to a point where a derivative doesn't exist. I can take the first few derivatives, but it doesn't always work out. So that's one example, an example of something could go wrong. It's possible to find a function that has no f to the n evaluated at 0. Bounding the function is not going to help if you are if you're on an interval containing 0. No, you don't have to memorize anything I'm telling you right now in this phase. It's kind of just me giving you things for curiosity's sake. So I might mention, oh, you need this for a function for a Taylor series to converge to a function, and this needs to work out for you to be able to say f of x equals a Taylor series. So a question that would normally come up would be, well, how can this not work out? Because derivatives are easy. We can always do derivatives. I'm showing you some situations where it won't work out. So here's something that we can't actually find a Taylor series for, at least not a Maclaurin series. You can kind of do it at other points on the real line, just as long as you open an interval that doesn't include the origin. Another example. Now, this one is kind of, I will admit it's somewhat cheating because the definition of this function would be very complicated, and I would have to kind of say it in terms of a gamma function, which again, many of you haven't seen, and it's probably not going to be mentioned to you until you take a course like differential equations, and maybe not even then. But let f of x be a function such that when we take its nth derivative evaluated at 0, we get n factorial squared. Right? Now, like I said, I can't write down a meaningful definition for that function now, but you can imagine there is some function out there where when I differentiate it n times, evaluated at 0, you have this. Then, its Taylor series would be the following. It would be the series, n goes from 0 to infinity, of n factorial squared over n factorial, not Taylor series, Maclaurin series, x to the n. This would just be n factorial x to the n. And this guy diverges for all x except, it's a power series that converges at one point, except x equals 0 itself. So if you have such a function, then the only way to actually guarantee that your power series is going to converge, your Maclaurin series will converge, is if you're literally at the point x equals 0. And at that point, it's not very useful if you have a series that literally only works at one point, not in general or on some interval. So that's kind of, so this is an idea of when the derivatives of a function gets too big. Once it starts getting larger than n factorial, it's something that's going to be much larger than n factorial, then when you throw it into the ratio test, you're going to get some limit that's larger than 1, and it's not going to work out for you. Here's another nice, sophisticated example. Something that does not suffer from either of the problems that I just mentioned before. It's going to be infinitely differentiable, and the derivatives are not going to be too big, but at the same time, no, we can find a Taylor series for it, but it turns out that the Taylor series will not converge to the function. So here's an example. In this example, f to the n too big, Taylor series only converges at one point. Which means f is not its Taylor series. So when your derivatives get too big, your Taylor series fail. Here's another example. Now this is a very famous example. And it's, this one answers the question, well, what if we can infinitely differentiate it and the derivatives don't get too big? Are we guaranteed to be able to find a Taylor series that actually represents the function, that we can say the function is equal to its Taylor series? And the answer there is actually still no. very famous example is the following. You look at the function e to the minus 1 over x squared, as long as your x is not 0, and you look at it as 0 if x equals 0. Now, here's what the graph of this function looks like. Looks like this. It's asymptotic to 1 over e, I think. Now, normally, this guy is undefined when x equals 0, but we actually filled in the point to be 0 when x equals 0. So this function is actually continuous everywhere, and it's also differentiable everywhere. So this guy is continuous and infinitely differentiable. And in fact, it has a Maclaurin series that converges on the real line. And so here's a function. I can actually find its Maclaurin series. It actually does exist for this function. And it converges for any x value that you want to plug in. And so you might say, well, if it has a Maclaurin series and it converges, does it actually represent this function? Does it converge to this function? And the answer is actually no. It converges to the 0 function. The Taylor series will actually be 0. You will have f to the n. The nth derivative evaluated at 0 will be 0 for this example. So your coefficients will always be 0, which means your Taylor series is actually a 0 series when x equals 0. But obviously the function 0, it only works out at that one point. So the Taylor series converges to this guy. So the Taylor series is this green line, or more specifically the Maclaurin series. The Maclaurin series is this green line when the function that that series represents is the red line. So this guy is nice in every sense of the word that we want to talk about being nice, but its Taylor series does not converge to the function. What happens here is that the remainder term, it did not actually approach 0. So that was the issue here. So it's a nice function, but if you come up with a formula for the remainder term, you bound it by something, turns out that thing does not approach 0. So those are some non-example. Yeah. I don't know. David's internet seems to be acting up. So like I said, these are just some things I wanted to mention for curiosity. I'll probably actually link to another video that talks about some things like this as well, for those of you who are interested, but yeah, you don't need to know that. Do I want to mention anything else before we move on? So that's it for 10.9. That's what I wanted to tell you. When does a Taylor series converge to a function? What are some things that could go wrong? It's essentially the takeaway. Now, none of this you have to have memorized, and the things that go wrong is kind of for curiosity's sake. You won't actually have to come up with any examples that does that. I'll only ask you about things that will exist, and if I ask you to find a Taylor series or a Maclaurin series, it's going to work, and chances are it's going to converge to the function that you found. So we'll only give you guys nice ones in that sense. But in the real world, a lot of things can go wrong. Yeah, it's probably you rolling dumplings. That's probably the thing. So yeah, section 10.9, very small section, very theoretical. You don't even really need to know it that much, but you should have some sense. You're expected to know, as a Calculus 2 student, that Taylor series don't always work out in the way that we want them to. Sometimes they'll only exist at a single point, which is absolutely useless for any function that you actually care about. No one's going to create a whole function where it only works at a single point on a real line and somehow use that in some application. That doesn't even make any sense. Or the Taylor series cannot work out and it can converge to something, but it can converge to some totally different function other than the function that you use to create the Taylor series in the first place, which again isn't very useful, right? If you want to write a function as a series, but the series converges to some other function, that's not also nice. There are also situations in which you couldn't even find the Taylor series in the first place because the derivatives either blow up, or they don't behave, or they actually don't exist after some finite number of derivatives are taken. So you have all of these things that could actually go wrong. But when you can find a Taylor series for something, it's so beautiful. It's so amazing, it's so awesome, and you get a lot of really nice things out of it, which is kind of where I want to take us next. This is section 10.10, where we're going to talk about applications of Taylor series. And we're really going to scratch the surface when it comes to this kind of thing. We're going to talk about some applications that we like that apply to calculus specifically, and the things that I'm going to test you on. But just like series in general, it's useful for so many things beyond calculus, it's not even funny. So it's not only a calculus thing that it's useful for, it's useful in other spheres as well. But we'll cover three. So the first application is the most important one in the sense that this is the application that I will expect you to be able to replicate. Like I'm going to ask you questions about this on a test or whatever that's going to look like, and I'd expect you to be able to replicate this. Right. So the first is to evaluate non-elementary integrals, which we've actually done some examples like that before, but we were kind of restricted to guys that looked like 1 over 1 minus x, the power series for that guy. Now we just want to generalize that idea, but it's the same idea as we've had before, but now I want you to be able to expand the kind of functions that you can do this on. That's one of the most important applications. It's something that would show up on a final. It's something that I would test you on for sure. Some other things that I want to mention though, because they're really cool and they're really neat, and some of them are things that you go to a higher math class, they'll expect you to know it, but you usually never see them before. That happens all the time. It's strange. Like, so at City College, we don't talk about complex numbers in Calc 1, Calc 2, Calc 3. In algebra, we don't do complex numbers. But yet when you get to differential equations, they expect you to know all about complex numbers. It's just one of those things. So I'm going to mention a couple other things that you're kind of supposed to be expected to know, even though almost no one talks about it ever before the point where they expect you to know it. So I'm just going to mention them. So one is Euler's equation. which gives rise to Euler's identity. So this is, and it's a specific equation that says the following. E to the I theta is equal to cosine theta plus I sine theta. This is so useful, it is not even funny, within calculus spheres as well as non-calculus spheres. Knowing that the exponential can be written in that way. And this leads to a nice equation that a lot of people know as Euler's identity, namely e to the I pi plus 1 equals 0. Which, if you were to Google what is the most beautiful equation in all of mathematics, most of the websites that you will see will list that as number 1. It is considered to be the most beautiful equation in all of mathematics. When we actually derive it, I'll kind of explain to you why it's thought that in such high regard. But yeah, proving this, just plugging in pi into this equation, Euler's equation, we can obtain that equation. Now, the third thing I want to talk about is the binomial theorem. Now, I'm going to talk about this very quickly, very hand-wavingly. In fact, 2 and 3, I'm going to get through both of these in like 10-15 minutes, just really kind of rush through them. Because technically they're not in our syllabus, but I think it's a really interesting application of Taylor's series. So this is generalizing how you can expand a binomial. So we're going to generalize how to expand, say, x plus y to the nth power, right? So it turns out that we know how to do this for n is any positive integer power. K goes from 0 to n of n choose k, x to the n minus k, y to the k. So this is called the binomial's theorem. It works for positive integers, n. I'm going to show you how it works for non-integers, and we're going to learn how to expand something like the square root of 1 plus x, or something like that. And it will turn out it would have to be expanded as an infinite series. So these are some 3 things that I want to talk about in this section. By the end of today, how much time do we have? Yeah, not much time left, so we probably will only get through 1 here, and I'll talk about 2 and 3 in the next lecture. So we kind of did something like problem 1, part 1 before, but we're going to do it again with a more challenging function, we shall say. So, 1, evaluate difficult integrals. Now last time we did this, I gave you an integral that actually was not impossible. You could do it by hand, it would just be extremely difficult to do so. So here, I'm actually going to give you an example that's impossible to do by hand. Find the Maclaurin series of f of x equals the sine of 2x squared. That's A. B. I would like you to estimate the integral from 0 to 1 over 10 of sine of 2x squared dx. Using a sum of 2 fractions. No need to simplify. C. Give with explanation. on the error of your estimate. So of course you're just estimating this, which means you're going to be wrong, kind of given a worst case scenario on how wrong you could be. So this is a very typical kind of problem. This showing up on a test or a final, a problem very similar to this showing up on a test or a final would not be a strange occurrence at all. I'll give you some time to copy that down or take a snapshot. But this is the kind of problem that I would expect you to be able to tackle. Yes, and that is fun. Functions that whose derivatives blow up or only converge, Taylor series convert to one point. They're fun, not very useful though, but you definitely do want to know when you're in one of these situations so you can know that a Taylor series probably isn't going to be useful. Not sure what funny name is referring to, but I think that was typed a while ago. Oh, Euler? Yeah. It's not a funny name. It's the pronunciation is different from what people usually think. A lot of people call it Euler. I hear especially biology kids call it that all the time when they learn about Euler's method in something. Can you teach me about Euler's method? Like, it's not Euler, it's Euler. It's a Swiss mathematician. He's a very such an important mathematician. It's not even funny. It's like he's a deity when it comes to math people, actually. He broke the mold before there was mold to break. Very prolific even into his old age, which is not typical of mathematicians. Most of them actually made their greatest contributions in their late teens, early 20s. This guy, his whole life, he was just dropping theorems like they were nothing. He was very prolific. And a lot of things are named after Euler. The number E is after Euler. E to the x, the base of that is Euler. Anyway, yeah. Now, we're going to do this. What I do want you to appreciate for this function is that the sine of 2x squared actually has no antiderivative. There is no function that you can think of that is a polynomial, exponential, trig, inverse trig, logarithm, or rational function, or any algebraic combination of those, who, when you take its derivative, will actually give you sine of 2x squared. Like, you can't come up with it. It's impossible. It's literally impossible to come up with such a function. So the integral, the indefinite integral of sine of 2x squared is actually impossible to calculate. You can't actually do it. We literally make up a function to be the answer because we can't actually express the answer in all the functions that we've seen up to this point in our lives. So, very difficult integral to do. It's called a non-elementary integral because you cannot express the antiderivative in terms of elementary functions, which you learned about in Calc 1. But we're going to approximate this indefinite integral. And I'm going to actually show you how something like Wolfram alpha might approximate it, and how it's going to tell you the error, how it knows how many decimal places to give you. Yeah, Euler's method is something in biology. It's used to approximate the solution to differential equations. Differential equations is super useful. It's useful in biology, chemistry, it's useful in everything. Like, one of the main parts of applied math is differential equations. So yeah, biology kids also need to learn it. When I teach Calc 2 for biology students, we talk about Euler's method in there. Okay, let's actually get back to this at hand because we don't have much time left. So yeah, hopefully you copy that down. Start with part A. Find the Maclaurin series for sine of 2x squared. Ideas, quickly. How'd you go about finding the Maclaurin series? Find the derivative. Good guess. So you might think of finding the first derivative, then the second, then the third, then try to find out a general formula for the nth derivative evaluated at 0 by plugging in 0 there. But one thing I want you to appreciate is that that's going to get mighty annoying very quickly, right? Because the moment you hit this with a first derivative, you have to use the chain rule, which is going to multiply a cosine of this by 4x, which immediately after that, you have to use a combination of a product rule and a chain rule every single time. It's going to get very messy, it's going to get very nasty, it's going to get that way very fast. So while this would be the way that we can build it from scratch, I would not recommend this method, especially not on a test. It's going to actually be not fun. That being said, on a test, let's say well, this should never happen, but let's say you forgot about the way that the more efficient way to do this. Because we asked for only 2 fractions, you would probably only need to do the first derivative, or maybe the first and second, in order to be able to do part B of the question. But part A, you'd still be wrong because you'd have to find this in general. So there's actually a better way. There's a better way than finding the derivatives and plugging in 0 and then finding a pattern. Other ideas? Define sine as it max or min? Not sure. How would you do that? Well, I know that the maximum of that is going to be 1 and minus 1 respectively for the minimum. I don't know how that actually helps though. Yeah, knowing that it hits a maximum of 1 and minus 1, I don't know how we can use that to help. Find a Maclaurin series. No idea? Substituting via identities, we're getting warmer. We're getting warmer. Now the question would be, what identity would you use? Double angle? No, we're getting colder. We're getting colder. One more guess. Half angle? No, it's not a trig identity. Here's a hint. We asked for the Maclaurin series of the sine of something. Do we see what to do now? Yes, that's all we do. Remember, we know, well, now we know after today, that the sine of x is this series. That's true. These guys are one and the same. So this should remind you of back when we were doing that example with finding the series for like 1 over 3 plus x and 1 over 3 plus x squared, and we did ln of 3 plus x. We actually used the fact that we knew about the 1 over 1 minus x to actually help us figure these guys out. We're doing the same idea here. I know about something that can help me with this guy specifically. So this guy can't help me with that guy because how am I going to express sine as a 1 over 1 minus x thing? But I know something for sine specifically. So all that I have to do is literally substitute. This means the sine of 2x squared is, well, I'm literally going to take this formula and replace x with 2x squared, because it's literally the same thing as sine. So it's minus 1 to the n of here. I'm going to plug in 2n, 2x squared raised to the 2n plus 1 over 2n plus 1 factorial. Now I can actually write that a little bit nicer, I suppose. So it's minus 1 to the n of 2 to the 2n plus 1 x to the 4n plus 2 over 2n plus 1 factorial. That is my Maclaurin series. Now here's another interesting non-example. So here's a Taylor series that we can find for this function. We know what it converges to. However, if we were to take the integral of this guy, it turns out it gives us a series that we can't actually figure out specifically what it converges to. We know it converges to something. We don't know specifically what that thing is. It's kind of weird. So that is the series. Now, we're going to use that, so let me copy this down on this side of the board here so I don't mess it up. So it's minus 1 to the n, 2 to the 2n plus 1, x to the 4n plus 2 over 2n plus 1 factorial. So that's the answer to part A. Which now, once you have that, so it's very rare that at this level, I mean, you might have to do it for homework, and maybe I'd ask you to do it for a quiz or something, but on a test, usually the function that you're going to be given, it's not going to be somewhere you have to build from scratch using the derivatives idea. But you should be able to use some other known series, which usually is going to be like the e to the x, the cosine of x, the sine of x, or the 1 over 1 minus x. So now what we're going to do is B. Estimate the integral from 0 to 1 over 10 of the sine of 2x squared dx using the sum of two fractions. Ideas here. Right, you just use the first two terms of the series essentially. So I know that this is equal to this series. That's what this is equal to. And in fact, because we have absolute convergence on the entire real line, I can actually switch the integral on the summation sign. I can think of this as the series of just the integral of the first two terms specifically, but of the integral of this more generally. So because of absolute convergence, I'm allowed to think of this as that. Now, this is what we call, as you might recall, term-by-term integration. integrate term by term, which basically comes down to, you can integrate each of these individually, but another way you can think of that is actually just integrating this formula. That would give you, n goes from 0 to infinity of, this whole part here is a constant, so you just differentiate the x, integrate the x part. So you add 1 to the power and divide by the new power. So you're going to have minus 1 to the n, 2 to the 2n plus 1 over 2n plus 1 factorial. And then you're going to have x to the 4n plus 2 over 4n plus 2. Then you're going to plug in 110 into that. And you're going to plug in 0 into that. So this is minus 1 to the n, 2 to the 2n plus 1 over 2n plus 1 factorial times 4n plus 2 times, well, 1 over 10 to the 4n plus 2. And then when I plug in 0, I just get 0. So now I can start approximating that. This is approximately equal to, just plug in two terms. Plug in n equals 0, and I would get 2 over 2 times 10 squared. Plus, plug in n equals 1, this will give me a minus 2 cubed over 3 factorial times 6 times 10, plug in n equals 1 to the 6. And that is my approximation as to fractions. Sum of two fractions. Got a question here. So was e to the 2x, you can find the Maclaurin series of e to the x and just plug in 2x? Yes. So, yeah, well, you wouldn't find the Maclaurin series. At this point, at the point when you're actually being tested on this, you should have that memorized. So yeah, so if I ask you if e to the anything, you can just take the series for e to the x and plug in anything. So you can use the 4 we know that have been memorized and find them. So we figured out the Maclaurin series for this sign because of the Maclaurin series for sine of x. It's this guy. I can integrate that term by term. Everything's going to work out because we have absolute convergence on the radius of convergence because we used the ratio test to evaluate it. And then, yeah, at this point, I integrate the x to the 4n plus 1. That gives us this using the power rule. Then I plug in the 1 over 10. Then I plug in the 0. So we end up with this. So that's our approximation as a sum of two fractions. So now, C, upper bound on the error. So that, I just use two fractions to represent a sum of infinite fractions. Obviously, I'm going to be off by something, right? We're going to have some error here. Can you tell me the worst case scenario, upper bound for the error? The next term, n equals 2, why? So with explanation, what would you explain? Why would the n equals 2 term give us, you forgot the reason? Well, there's literally a theorem that tells us that this. It's one of the estimation theorems, which is kind of named after the series that it's being applied to. This is minus 1 to the n of blah. So it is what we call an alternating series, which means we can use the alternating series approximations here. The third term tells us how good an approximation with the first two are. So I just added the first two terms. It's an alternating series. The magnitude of the third term tells me how far away from the answer I actually am. So pretty much an upper bound for the error is going to be the third term, which is when I plug in n equals 2. So if I look at the magnitude of my error, it is going to be less than or equal to the n plus second term. Or in this case, plug in n equals 2, the n plus first term. Plug in n equals 2 specifically, because I'm doing for the first two terms. So plugging in n equals 2, I would get 2 to the 5th over 5 factorial times n equals 2 here. That would give me 10 times n equals 2 here. That's 10 to the 10. So that's how close I would get to the answer by using the first two terms. So this is going to be, just to give you an idea, let's actually see in decimal form. Where's my phone? See in decimal form how close we actually got here. Okay, so we are off by 2.67 times 10 to the minus 12. So that's like, so how close is this? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 2, 6, 6, 6, 6. This is an upper bound for our error. So of course on a test you won't have a calculator, so this is what you'd write. The error is going to be less or equal to that, but just for you to see how good just adding two fractions is in this case. That's how much we're off. Which means when you type this, if you plug this integral into Wolfram alpha, it literally is going to convert it to a series and add 2 fractions, because Wolfram alpha usually just gives you the first 6 decimal places. And that's good enough here. It's just going to add those 2 fractions and give you the first 6 decimal places of the answer. And that's how it did the integral, which is pretty nice. Yes, yes. Yeah, pretty good approximation. This series converges to the function very quickly. But you can also realize that we actually didn't. Sine of x and x are very close when your x is close to 0. We're literally on the from 0 to 1/10. So within that small window, you don't expect to get very far with your sine function. Your sine function has a slope of less than 1 at that point. It's not going to grow very fast. So just adding the first 2 terms of the series can get you close to the answer. But yeah, that's how you'd find the error. So that's a complete problem that you might do on a test. You can just say, by the alternating series approximation theorem, upper bound for the error is blah. So here's what I want you to do, because we're done now. But for next time, just to make sure you can do it, repeat above for integral from 0 to 1 of e to the minus x squared. So that guy is, again, an integral that we can actually compute by hand. Not because it's hard, but because it's impossible to write it down in any function that we know about. And I'll do this next time, but try to prove Euler's equation. That is the fact that e to the I theta is equal to cosine theta plus I sine of theta. And the hint would be, use Maclaurin series and kind of see if you want, you can figure it out. By the way, here, your I is the imaginary unit. I is equal to the square root of minus 1. You can use that definition. It's the imaginary number, the imaginary unit. So do these for next time. I'll do these problems at the beginning of the next lecture. We'll talk about the binomial theorem, maybe some other cool applications, and yeah, that's it. Any other questions before we go? We're pretty much done. Okay, yes, you guys stay safe too. Yes, David's got to eat his dumplings. He worked hard on them. Harder than he did in this class. Okay, all right. All right. Stay safe, guys. Try these 2 for next time. Read over the notes. As I said, the things you need to know are, you need to memorize those 4 Taylor series. You need to know how to do a problem like I just wrote on the board. You need to know how to find Maclaurin series in general, as well as use known Maclaurin series to find series for new guys. The other theoretical stuff, it's really, things are expected to know, but I'm not going to directly test you on it. But in future classes, they'll kind of expect you to know this out of the blue. So yeah, we will wrap up there. I'll stop the recording here. Bye, take care. And I will stop the recording here as well.